All right, welcome back to my channel. In this series of videos, I show people how I do native development on directly on a Commodore. This is a Commodore 128, which you can't see in the video, but that's a Commodore 128, and this is Turbo Macro Pro. So in this video, I have been working on a utility for C64 OS that lets you look at the details of a file, the currently open file, or the currently selected file in the file manager. And it will show you the file name, which you can edit, the file type, size, date and time of modification if it's available. And it also shows you the lock status in a checkbox and lets you toggle that. So I can actually show you, if you could see this. This is the utility that I've been working on. Now I'm kind of experimenting with an alternative layout, but for now I've been implementing this one here. So basically you get the file name, and you have a checkbox for lock, and then you have some buttons for renaming the file. You have its size, its file type, and the date and time. So it's pretty basic, but this is what we're focusing on right here. This is the lock checkbox. So in a Commodore file system, a file has the ability to be locked, and a locked file can't be deleted, and I think it also can't be opened for write. The only thing that it can be done, this is a bit weird to me, I feel like this might be an oversight of Commodore DOS, but you can save a file using the @ command, which is the save with replace, and I believe that works even if the file is locked. So a locked file is not perfectly safe from being overwritten, but it helps. In order to implement the ability to flip the lock bit in a utility, we need some code that will let us actually flip the lock bit in the file system. Now, how exactly you do that depends a lot on the DOS on the device that you are supporting. So C64 OS can run from an SD2IEC, an IDE64, the CMD family of devices, including the CMD hard drive, CMD FD floppy drive, and the CMD RamLink. There should be support also for the CMD RAM drive, but I don't know anybody with a RAM drive to even test that on. And C64 OS also supports 15, 41, 71, and 81 for data purposes. You can't boot from those, but for data purposes, you can access those devices. Now, the SD2IEC is based upon a FAT file system, and basically it just has no support for locking of files. So, whatever technique we would use, it's not supported on SD2IEC. So we're going to basically just disable that functionality if we know it's in the user interface. We'll gray out the checkbox. Now, if it's one of the CMD devices or an IDE64, those are kind of more modern devices as far as Commodore 8-bit disk drives are concerned. And they actually have a special DOS command, which is the L, it's just an L, which stands for lock. So you can issue the L command, so you go L : and then the file name, and that will XOR the lock bit on the matching file. On On the legacy devices, 1541, 71, and 81, there is no such command, and the only way to modify the lock bit is basically to search manually through the directory entries, find the directory entry with a matching file name, and then the lock bit is bit 6 of the byte that holds the file type. So PRG, seek, user, rel, those file types. It's the same byte, but the file type is only in the low bits. Bit 6 is for the lock bit, and then bit 7 is for whether the file is open or not. So what we want to do, what I decided to do, was I'm going to write a relocatable library in C64 OS so that any utility that wants to mess around with the lock bit can use this library. And also it's nice because it takes the code and it kind of segments it out of the utility, so it makes the utility a little bit lighter weight. And it's just a perfect candidate for a relocatable library. It's a nice contained little chunk of code. And so what we're going to do is we're going to look at how I've implemented that. Now, I must be honest, I didn't really know how to do it. I mean, I had a basic idea, but I searched around on the internet to see if anybody had already implemented this, and I found someone called Old School Coder on GitHub had implemented a kind of a command line disk operating system, which is that allows you to, issue commands in a more modern kind of command line style way, and then it backends on the Commodore DOSes, and it has support for a couple of extra features such as locking. And so it so happened that this code repository on GitHub actually contained a routine that would flip the lock bit. Now, it was kind of deeply integrated with the way that guy's system worked, and it also didn't have support for the special CMD or IDE64L lock command. It also made certain assumptions, like the ability to open and close the command channel whenever it wanted to, which is a no-no in C64 OS. It also used like a hard-coded logical file number for the buffer channel. We'll get into that when we look at this, when we dig into this code. But it made certain assumptions like that. It also didn't have proper support for the 1581. So I basically I just used that routine as kind of a guide for myself, and I've more or less completely rewritten it with support for C64 OS Technologies. So in C64 OS, you will pass in a file reference, not a pointer to a file string, but you'll pass in a pointer to a C64 OS file reference. This library will use the C64 OS detected drives library. It'll also use the file kernel modules error checking, which will update the status bar, and it'll give us what command channel logical file number is already open for the device. And of course, it's relocatable, and it has support for all the devices, and so on. So, without further ado, let's just start walking through this code, and I will describe how it works. So we'll jump to the bottom here first, just to see how many lines. So the whole library is 434 lines. So it's not bad. It's fairly small and manageable. Yeah, maybe I'll mention this first. Initially, I wrote this to be simply a lock-unlock library. But as I was thinking about it, because the lock bit is in the same byte as the file type byte of the directory entry, I thought, well, maybe this library could be extended to offer functionality to let you change the file type of a file. Now, I'm not sure whether I'm going to have the room to fit that into this library, simply because there is that special DOS command for locking and unlocking on, say, IDE64 and CMD-HD. But in order to support changing the file type, I would have to add a fair bit of code. So I'm not sure whether I'm going to do that, but it's a thought, right? It's a thought. So to start with, basically all basically all C64 OS programs, libraries, drivers, application binaries, and so on, start with this line here. This draws in a header for giving us the definitions for the kernel modules. But in addition to giving us the headers for the kernel modules, it also defines some very important relative include macros. So these relative include macros make it really, really easy for us to include critical files, headers and constants files. And it also abstracts their location, which is really good. It makes it easy to type, but it also abstracts their location. So next, following this is the regular syntax for an include, and it has to have this kind of absolute path. But this is the only absolute path that's necessary. And beyond that, the macros abstract the paths for you. So here we have a series of the includes that we're going to need. So the macros are basically include S. Those are for constants. Include K. Those are for kernel ROM includes. And there's one other that we'll see later on. It's inc H, which is for headers. Headers are specifically for defining the addresses of routines that you can jump to, whereas the ones that end in S are they just define commonly used values, but not typically things that you would jump to. So these are just common ones. They bring in common features that we will use often. These two bring in the ability to work with files and channels, I/O channels from the kernel ROM. And this is the only one here that is specifically for a C64 OS kernel module, file module. So this is a relocatable library. So a relocatable library must start with a jump table entry, and the first one must jump to something that is found within the first page of this relocatable library. That is simply a requirement of C64 OS relocatables. Now, as it happens, because this is a relocatable library, libraries have an additional requirement to function as a library, and that is that their very first jump table entry is to a link routine. So the link routine it's basically an init for the library. In fact, you could call it init if you want. I call it link here, but because it links things together. But effectively, it's init. The second jump table entry, therefore, is the actual the routine that you would call in order to do what the library does, toggle the lock bit, and of course, libraries can have as many jump table entries as they want. So following the jump table, again, this is pretty standard practice for me. I define all of the variables that are going to be used by the library. So we can go through a couple of these here. I have a comment here that CMD, HD, FD, and RamLink uses the LDOS command, which simply XORs the lock bit. So we have the device number that the file will be on. CMD LFN is the command channel logical file number, which will be dynamically given to us. Buff logical file number, that is the buffer on the device that we're going to be interacting with, so that you need a channel to the device to communicate with the buffer of data. That's also going to be dynamically generated. Next, we have the current track and sector that we're working on, and then we have the next track and sector. So the track and sector pointers, the sectors are chained together such that the first 2 bytes of the current track and sector, so you have an initial track and you have an initial sector, and the first 2 bytes of that sector are the track and sector pointer to the next sector in the chain. And if the track byte is 0, that indicates that there is no more, that's the end of the chain. There are no more sectors that follow this in the chain. So when we load in a sector, the first thing that we'll do is we'll pull the track and sector bytes out of that sector and store them in the next track and sector variables, so that then we'll scan the current track and the current sector rather, and if we can't find what we're looking for in that sector, then we'll take this next track and sector bytes and copy them into current track and sector, and then proceed to load in the next one. FType is the file type byte, which contains it contains the type bits, the lock bit, and the open bit. File name, this is a 16 byte buffer, which we'll use to compare the file name of the file we're looking for with the file name that we're pulling out of a file entry in the sector that we're looking at. FN in sec is the file names index in this sector. So a sector is 256 bytes, and it's divided into 8 32-byte entries. So before we go any further, this is the CMD hard drive manual. And very conveniently, because the CMD hard drive supports emulation partitions for 15, 41, 71, and 81, it gives us all the relevant track and sector layout data for those types of disks, for those file systems. So we can see here, this is common formats used in all partition types. So this will be 1541 and 71 partitions, 1581 partitions, and native partitions. And of course, by partitions, that also means real physical 15, 41, 71, and 81 disks. So what we see here is this is the layout of one sector that's used in a directory. The first 2 bytes are the track and sector pointer, and it says right here that the track pointer's next directory block of 0 indicates that this is the last block, which is what I just mentioned a moment ago. Following the first 2 track and sector pointers, we have these file entry 1, 2, 3, 4, 5, 6, 7, 8. Now, because 256 bytes divided by 8 perfectly divides by 8 to have 8 32-byte entries. The problem is that the 0th entry has the first 2 bytes already occupied to chain the whole block, the whole sector, to the next sector. So what that means is that the first directory entry can only use 30 characters of those 32 bytes. Therefore, it makes sense that every file entry has only 30 bytes. So it's divided into 8 32-byte entries, but the first 2 bytes of every entry are simply marked as reserved, and they're always 0. So, if you want the 4th file entry, you go 32, 32, 32, 32, and then you skip the first 2 reserved bytes. So we'll come back to this in a second to look at what a single file entry looks like in a directory block. So this file name and index in the sector, so basically you're going to have an index of 0 through 7 for the 8 possible file entries that occur within one sector. And that's what this byte's going to hold. So lock bit, this is just a constant showing us that bit 6 is used to be the lock bit. So next we have this U1 command and U2 command. So it's a little bit complicated, and I'm not going to get into it, but there is a difference between the command block read, block write, and U1 and U2. They're similar, but they're subtly different. U1 and U2 are a little bit more generic, where they simply read all the data in the block and they write all the data in the block. But the block read and block write commands themselves have some sort of nuances that make them really only useful under very specific circumstances. So, but the idea here is that there is this U1 command that lets you specify a. Actually, before I say that, there's a special file that you can open whose name is #. So if you open a channel, one of the standard data channels, 2 to 14, on the storage device, and instead of opening it with a standard file name, you give it the file name of #. It tells the device that this channel is not a channel that will read data sequentially out of a file to be opened, but rather it associates this channel number that you're opening, 2 to 14 again, with a buffer, a 256-byte buffer in RAM inside the storage device. And by default, it'll automatically allocate a 256-byte buffer, and it'll associate that RAM buffer with the channel that you have specified. And then it has a buffer pointer, which it initializes to 0, I think. And every time you read something from the channel, instead of reading from some file, it's actually just reading whatever is in that memory buffer. And every time you read, it increments the buffer pointer by 1, so that as you read, you're sequentially reading bytes out of that memory buffer. Now you can issue a BP, which is buffer pointer position command, and with that command, so you go b-p colon, and then you say the channel, and then an index from 0 to 255. So it'll take the channel that you've specified, and it'll use that to figure out which buffer is associated with that channel, and it will change the buffer pointer for that particular channel and buffer. And then subsequent reads will start reading from wherever the buffer pointer is. So the U1 command works in conjunction with an opened buffer to allow you to read any arbitrary track and sector from anywhere on the disk. One sector is 256 bytes, the exact same size as the allocated memory buffer. So U1, you specify the channel, which links you to the memory buffer, and then you specify the track and the sector to read, and it will read the contents of that track and sector. Doesn't matter what file it belongs to. Absolutely doesn't matter. It could be part of the directory, it could be part of a file, it could be part of the BAM, it could be a completely custom file format that you have implemented on a disk. It doesn't matter. It's just any track and sector. It'll read that entire sector and put it in your buffer, in the memory buffer that's allocated for that channel. U2 does exactly the opposite. It takes the memory buffer that's associated with the channel, and it writes it to whatever track and sector you specify in the U2 command. Okay? So that's the general idea. So actually the general idea is you open a channel with a buffer. You issue a U1 command to read in a directory block. You use the buffer pointer command to move the buffer pointer from file name to file name to file name to file name through the 8 file names that are found within that directory sector, that directory block, and you read through the file names looking for the file name that matches the one that you care about. And if you find it, well, perfect, you are in the sector that you need, in which case you can then move the buffer pointer back to the file type byte of this entry, modify the lock bit, and then you take the entire sector and you write it right back to where you got it from. And if you read through the entire sector and you don't find a matching file name, well, then you have to use the U1 command to read in the next sector in the chain. And you just keep doing that until eventually you find your file name. Or you don't find the file name, in which case you return with an error. So so that's it for our variables. So the first routine that's in a relocatable library is this link routine. So technically, this link routine gets called automatically by the C64 OS dynamic shared library loading system. Okay, so you load a library and it automatically calls link. If two things try and load the same library, the link method gets called a second time. Now sometimes that's good. Sometimes you want the link method to get called a second time. But sometimes there are at least some portions of the link method that you don't want to be called multiple times. So what this link method does is it initializes the externs. This is a very standard pattern in C64 OS with anything relocatable. Anything, not even relocatable, but applications and utilities and everything basically that needs to use the C64 OS kernel goes through this init externs phase. And what that does is it links a table of calls to the C64 OS kernel. It links those calls to where the kernel modules actually reside. So that helps for maintaining forwards compatibility with new versions of the kernel that will eventually be released. So let us skip down to externs. So using Turbo Macro Pro, I can hit the back arrow and then I to jump to a label. So I'm going to jump to externs, and I'm just going to make a mental note that we're currently on line 59. Or the routine link. We could jump back to link using the label. So we'll jump to the label externs, and you can see that this is right at the end of the file. So here we see once more one of these macros for include, but this one is inc h, so that's a header. So that's going to bring in the file header for the file kernel module in C64 OS. And then we're only using actually 2 kernel calls. This entire library only uses 2 C64 OS kernel calls. It uses a few kernel ROM calls, but so finit is file init. We'll see what it does in a minute. Ferror is file error, so it checks the error channel and updates the status bar. And these macros, these constants here come from the file header, and these constants come from the file header. This system call is a special macro that builds this table in a way that these will get converted into jumps to where the kernel calls actually reside. And then we have a terminator on the table. So let's return to line 59. That was back arrow N. It's funny, my muscle memory just tells me what to do, and if I have to actually think about it, I forget what letter it is. So it's back arrow N will go to a number, so we can go to line 59. So the thing is, though, that we actually only want to link the table once. We don't need to link this library. We don't need to initialize the externs table more than once. So after we've initialized the externs table, I take the low byte address of this RTS and I write it back into the jump table so the jump table link entry. So the next time, if somebody else tries to load in this shared library a second time, when it gets loaded, it will call link, but this link will have been updated to point directly at this RTS. So subsequent calls will not re-initialize the externs table. So there you go. Next, this is something really cool that I got from that GitHub code repository. Very clever. I like the idea of using certain basic routines. So the basic ROM, I mean, it's not like we're actually writing code in BASIC, but the basic ROM is full of all kinds of little snippets of code that get used. And so why not use some of those routines? So deci out outputs a decimal. So if you have an int in your assembly code, but the DOS command of the drive needs like an ASCII or a PETSCII number. Now, why does it need a PETSCII number? Because typically you actually type this as strings from BASIC, right? So if you want to give like a buffer pointer command, you're actually typing B-P, and then you might type the number of the channel that you're using. So you'll be like, 10 will be the channel number. But what you're actually typing is a 1 and a 0, which are PETSCII 1 and PETSCII 0, right? So the DOS is actually getting PETSCII numbers. But in your assembly program, it's like, well, you probably have the channel number as an int. So somehow you have to change the int to a decimal number, like a PETSCII number, and send it out to the channel. Well, as it happens, there's a basic routine at BDCD which does precisely that. It takes a 16-bit int in the X and A registers, and it will convert that 16-bit int into a 1 to 5 digit PETSCII number, and it will automatically send it out whatever is the current output channel. So that's very convenient. And similarly, there's this AB1E basic routine, which takes a pointer to a string in A and Y, and it simply outputs the whole string up to a null byte, a 0 byte. So that it sends that out to the current output channel. So that's a pretty convenient routine as well. I mean, we could write the routine ourselves, but why not use the basic one, right? Now, you may wonder what's going on here with this Inc and Dec 01 stuff. So in C64 OS, by default, the basic ROM is patched out. By default, the standard running condition is kernel is in, IO is in, basic is out. Now, in a utility, the utilities are run from behind the kernel ROM, so it's a little different. When a utility's code is running, everything's patched out. Now, how therefore does a utility call a routine that is in the kernel ROM? Well, it does that by setting up a redirect. Now, that's a little outside the scope of this video, but basically it calls a redirect, which patches the kernel in, then jumps into the kernel, which returns, which patches the kernel out, which returns back to the utility code. Very, very similarly, if we want to access something that's in the basic ROM, we can simply increment the processor port by 1, which will go from the standard state of the kernel and IO being in, and by incrementing it 1, we'll bring in basic. Then we jump to the basic routine, and as soon as this returns, we decrement 01 to patch basic back out, and then we return. So we do that for both of these basic routines. Now, if this code is being called from under the kernel ROM, here's what'll happen. Well, first of all, this library will get dynamically loaded into somewhere in memory that is not under the kernel ROM. But let's say something in a utility is going to call into this library. In order to call into this library, it will have to set up a redirect into this library. So that is going to patch in the kernel and IO. Then it's going to call this library. Then this library will patch in basic. Then this library will patch out basic. And when this library returns, it'll go back to the redirect. That'll patch the kernel and IO out, and then it'll go back to the utility. So it still works, and it makes sense here that at the level of this library, it makes sense that we just assume the standard operating state of kernel and IO are in. We patch in basic, we patch out basic to get back to that standard state. Okay, so next we have the actual meat and potatoes of this library, which is to toggle the lock flag. Now, originally I thought we should be able to pass in what mode we want it to be. We want it to either set the lock or we want it to unset the lock. The problem is that the DOS command in IDE64, CMD, FD, HD, and RamLink, they actually don't let you specify whether you want to set or unset the lock. Their L command XORs the lock bit. So it always flips it. If it's on, it turns it off. If it's off, it turns it on. So I wanted to follow that behavior and simply make that behavior available to the legacy devices. So there's no more ability to specify. It didn't really make sense anyway, right? I mean, if it is locked, you're going to call a routine to lock it. It doesn't make a lot of sense. I mean, you typically want to invert it, right? So if you've in the user interface, if you have a checkbox, the checkbox is on because you've already read from the storage device. You've already determined that it's locked when you read in its file size, and you read in its file type, and you read in its date and time. You read in its lock state, and then the checkbox indicates that it's on. When you check the checkbox off, it flips the checkbox and we'll call this toggle routine, and the two will be in sync. And then you check the checkbox on, and it calls this routine, and the two will be in sync again, or will stay in sync. So, okay, so the first thing here is that we use a register pointer, which in C64 OS is the X and Y registers, X being low, Y being high, to pass in a pointer to a C64 OS file reference. A C64 OS file reference is a standard structure that lots of things in C64 OS can use, from utilities to libraries to the kernel itself. They all make use of this standard file reference structure, which encapsulates the device, the partition, the directory, the file name, and then can also contain some extra data about, for example, the size of the file, whether the file is opened or not opened, and so on. So we pass in a pointer to a file reference, and we back up that file reference to one of our, to a pointer, a zero-page pointer. So next we call the C64 OS kernel's file init, which already has this which also takes a reg pointer to the file reference. So that's already ready to go. And what that does is it basically initializes the drive, the correct drive as specified by the file reference, to be in the current, to set the current partition and current directory, so that all the commands that follow this will be relative to the directory of the file reference. Now, if the file reference is to, say, a 1541 device, that's perfectly fine. FINIT handles that. Now, if there's some error, like if the file reference is to a device that doesn't exist, we'll get an error, and we simply return, and the carry will be set as if that's an error, and the carry being set from this routine indicates an error. In addition to using the carry for whether there's an error from FINIT, assuming that the carry was clear and there was no error, FINIT also gives us, in the X register, the logical file number that has been assigned to the command channel, which is already open and stays open all the time for this device. have some coffee. So unlike how a lot of Commodore 64 programs will kind of open the error channel when they, or the command channel when they want, send a command, and then close the command channel, you can't do that in C64 OS. The reason is because when you close the command channel on any Commodore 8-bit storage device, when you close the command channel, it implicitly tells the device to close all open files. And of course, in the context of an operating system where there's more than one process going on, you never really know that there isn't a file that's currently open for some other reason. So basically, if you use the drives utility to bring a new drive online, it opens the command channel to that device and it assigns it a logical file number for that command channel. And when you finit, there is a way to get that command channel programmatically, algorithmically rather. But if you use finit, it very conveniently returns you in the X register the command channel's logical file number. So we stash that into one of our variables above so we can reference it later. Next, what we do is we read the device number from the file reference and we store that in one of our variables up above. And next, C64 OS maintains a detected drives map. We take the device number from the file reference and we look it up in the drive map to see what is the detected device type. Now, if there's no device for that device number, that's 0. So 0 means, a 0 in the drive map means there is no device on that device number. 1 is used for a foreign device. So there might be some device on the bus that is just completely unrecognized by C64 OS. If it is, it gets a device type of 1, dev foreign. We don't know how to handle it. I don't know how to handle it. C64 OS doesn't know how to handle it. So basically, we check to see whether the device number is greater than the foreign device number. And if it is, we can proceed. But if it's a foreign device or no device, we have to immediately return with an unsupported device type. Set carry error. Can't toggle a lock bit for a file reference to a device that we don't recognize or that isn't there. Next, the SD2IEC is the only device type that doesn't support file locking. So I have to make an explicit check here to say, is the device type SD2IEC? If it is, we simply branch back to this unsupported device, set carry, and return. However, if it is not an SD2IEC, the next thing that we worry about here is it a legacy device or is it a modern device? And the way that the device numbers are set up in C64 OS is basically if the high bit is set, bit 7 is set, it's a modern device that supports partitions and directories. If the high bit is low, it's a legacy device. No partitions, no directories, and no lock command. So I'm comparing that explicitly to the lowest device number that we have with that sets the high bit high. So the CMD FD is basically device number 128. So that's all zeros except for the high bit is set. So if it's less than the CMD FD, it's a legacy device, and we're going to skip over and carry on with all the legacy device code that we need to implement. However, if it is equal to or greater than the CMD-FD, we can simply make the lock command. We can simply issue the lock command. That'll work for the HD, the FD, the RamLink, the IDE64. Now the SD2IEC is up in this range of device types, but we have explicitly excluded it. So let's just let's assume that it is one of the more modern devices, and we'll just jump directly to the lock command. And we'll come back to line 122 afterwards. So we'll hit back arrow I to jump to that label. CMD lock. So issue a special DOS lock command. So to do that, we'll start by clearing the channels. And then we grab the command channel logical file number, which we don't know what it is, but C64 OS gave it to us when we did the finit. So we grab that and we say checkout. Now this is a kernel ROM call. So we're doing, this is like really standard C64 kernel programming. We grab the logical file number in the X register, call checkout, and that sets that logical file number as the current output channel. Then we char out an L, we char out a colon, that's the lock command. And the only other thing to do is to char out the file name that we want to send with the lock command. And we do that by looping through the file name that is found in the C64 OS file reference structure. And we've already got a pointer to that, a 0-page pointer. So we start with an the file ref's name index. And we simply read the name out of the file reference structure until we hit the 0 byte. But if up until we hit the 0 byte, we simply keep char outing the file name and looping to get the next character in the file name. And when we hit the null terminator on the file name, we branch down to here and we simply clear the channel. So clearing the channel, now remember, this is the command channel, it's always open. So we're not going to close that channel, but calling clear channel sends the very low level IEC signal on the IEC bus to the device to indicate that we have we've finished sending data to the bus, and this clear channel will actually cause this lock command to be executed. Next, we make another C64 OS kernel call ferror. What that does is it then reads the error channel and parses it from the storage device, and it will update the status bar as well. So if it's a 00 OK, so a lock command should result in a 00 OK status. And ferror also returns in the accumulator the status code. So we can compare that to 1. And if it is less than 1, aka it's 0 for OK, well then that will clear the carry and we can return and everything's okay. But if it is equal to or greater than 1, well, that's not an OK. So it's some kind of an error, but that also sets the carry. So simply by comparing to 1, we can set the carry on error or clear the carry if it's okay. That's pretty much all you need to do to support the more modern storage devices. Super, super easy, right? We basically just open the command channel for checkout on the command channel for the device, send out L colon, send out the file name, clear the channel, check for an error. We're done. Very, 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 very straightforward. Now we're going to bounce back to, I think it was line 29. It was not line 29. Was it 129? Nope, wasn't that either. No problem. My memory is failing me. Oh, 122. Yeah, it was 122. Okay, now if it is a legacy device, so we're going to skip. If it's less than the CMD FD, it's a legacy device. We're going to skip down to here. So it's going to be either a 1541, 1571, 1581. Those are the only 3 legacy devices that C64 OS supports. And according to the manual right here, 1541, actually it's right here, 1541 and 71 file systems have their first directory entry found at track 18 sector 1. So 1541, 71 both use track 18 sector 1. But the 1581 partition or file system, its first directory block is at track 40 sector 3. Now, native partitions also use a track and sector that's unique for their start of directory. However, if it really is a native partition on if it's a native partition, it really is on a CMD device. And if it really is on a CMD device, we're using the lock command, so we don't need to worry about where the track and sector are for native partitions. We just care that if it's a 1541, we got to use 40 and 3. So that's what we do here. We compare explicitly to see whether the device is a 1581. If it's a 1581, we skip down to here. We set track 40, sector 3 into Y and X respectively, and then we fall through to writing those into our variables at the top of the file, current track, current sector. So current track and current sector are basically we're going to set the starting track and sector as the current track and sector. If it wasn't a 1581 though, well, then we'll use 18 and 1 for either 1541 or 1571. Then we'll branch down here to write 18 and 1 into those variables. Okay, next we need to open the channel for the memory buffer, to the memory buffer. Now, in the routine that I pulled this in the GitHub version of this routine, it was just hard coding channel 10. Well, you can't do that in C64 OS. Why? Well, because you don't know who else has got a file open. Basically, you can't use a channel, you can't just assume that a channel is unused because there are other things running at the same time as your code. So the file module, the file kernel module, when you say open a file for read, it actually has this loop just built into it to auto-detect an available channel. And I have re-implemented this very short routine here because we're not doing a standard read. This is a pretty non-standard use case. We're opening a memory buffer, so it's not built into the file kernel module. But anyway, I have re-implemented the same detection loop that's used by the kernel file module, the file kernel module. So basically what it does is it starts with the lowest possible logical file number of 2. Well, it actually starts with 1, but the very first thing we're going to do is add 1 to it. So it starts with 2. Then it checks to see how many files are open. And if there are currently no files open, that is that if the file table is 0, it will leave here automatically. 2 is perfectly acceptable to use. Otherwise, what it does is it starts with how many files are open, and it looks at the logical file table, and it checks to see whether 2 is at that index of the table, the last index of the table. If it finds it in the table, well, you can't use 2 because that's already open in the table. So it branches back up to here to increment 2 to 3 and to check again. But if it doesn't find it at that spot in the table, well, then it loops backwards through the table. So it starts at files open. Let's say that there are 5 files open. Okay, so it's going to start at index 4, and then it'll check 4, 3, 2, 1, 0. And if none of those indexes contains the file number 2, then 2 is acceptable to use. But if it finds 2 at any of those indexes in the open file table, then it increments 2 to 3, and then it repeats, and it searches the logical file table from 4, 3, 2, 1, 0 to see if 3 is somewhere in there. Eventually, though, it will find some logical file number. It'll find the lowest logical file number that is not taken. And it'll follow the end of this table with the logical file number that we can use in the accumulator. So what we do is we save that as our buffer logical file number to a variable up above, because we're going to need to refer to it later. We use a matching logical file number with an I/O channel. And then we use the device number, which we pulled from the C64 OS file reference, and we set LFS. So set LFS is a kernel ROM call. Again, this is totally standard Commodore 64 kernel programming. Next, we are going to set the name for the file that we're opening. So we set a pointer to bf command, which is literally just the hash symbol. And the accumulator says that there's only one character in the name, and so we set name. So that's just a pointer to the hash character as the file name. And then we open. And that's going to tell this is going to tell the device, we're not trying to open a file. We're actually trying to open a memory buffer. So it's going to allocate a memory buffer. It's going to set the buffer pointer, or give us a buffer pointer for that memory buffer. And it's going to associate that newly allocated memory buffer with this logical file number that we have dynamically selected. Okay. Next. File names in a C64 OS file reference are C strings. So they're all the characters of the file and then terminated with a 0 byte. But that's not how they're stored in the directory entries on a disk. On a disk, there's exactly 16 characters. And if the file name is less than 16 characters, then the file name field is padded out with A0, which is actually a shift space in PETSCII. So what we are going to do, I also got this from the routine from GitHub, so thanks to Old School Coder for this idea. So basically what we do is we take our file name buffer, which is in the variables up above, and we fill it with A0. We just go fill it with A0. And then what we do is we loop over the file name from the file reference, C64 OS file reference, and we copy just the number of characters in the file name over top of those A0 padded bytes in the file name buffer. So if the file name in the C64 OS file reference is, say, like 5 characters, then we start by filling the buffer, 16 characters all filled with A0s, and then we write just the 5 character file name into the over top of the first 5 characters of the buffer, and then the rest are all A0s. What that allows us to do, by the way, is it basically means that the 16-character file buffer will be precisely what we need to look for in the 16 characters of a file entry in a directory block. So, 16-character file name buffer with the A0 padding is precisely what you're going to find in a directory if they match. So after we've done all that setup, we've got our buffer open, we've got our file name put into the file name buffer, we've figured out what device it's on, we've figured out if the device actually supports the thing and supports locking, all that stuff. Everything is done. We fall through to loading a tracking sector. Now, the tracking sector the current tracking sector have already been configured for this device. So now we're going to issue the U1 command. So the U1 command is going to read the sector. We're going to read the sector from the current tracking sector. We're going to read it into the memory buffer. So we clear the channel. We read in the command logical file, the command channel's logical file number, and do a checkout to set the command channel as the outgoing channel. Next, we load a pointer to the U1 command, which is literally just U1:, and then we say this do UX command. Now, why do we say do UX command? Why not actually have it in line here? Because the U1 command and the U2 command are literally identical, except for the command itself, U1 versus U2. So it's this routine here, do UX command, is shared between U1 and U2. So let's see if I can remember, 204. So we're going to jump down to do UX command. So so this is just telling us what does this command expect as input? Well, we need an AY pointer to the command string, the U1 or U2 command string. The buffer's logical file number has to already be set. Of course, it has been. And it's going to make reference to the current track and current sector. So it immediately jumps to the basic string out. That's going to output the command string to the command to the currently configured output channel. That's the command channel of the device. Then it is going to do this decimal out, this decimal conversion int to PETSCII number, and then send that out to the command channel. So it's going to send out the buffer logical file number. Next, it's going to do this UX command. This is kind of a common piece of the command. It's common between U1 and U2. It's just comma 0, comma 0, comma. So we output that as a string. Then we grab the current track and we decimal output that. We output a comma. We output the current sector. And that's the complete U1 command. It's also the complete U2 command. And so that's going to load in this track and sector into the memory buffer that's associated with this logical file number. Okay. We're going to jump back to where we were, line 202. So now we have the current track and sector in a memory buffer. So we have just loaded in a brand new sector. So what do? We are going to initialize our file number in the sector index to 0. And with 0 in the buffer, we're going to set the buffer pointer to 0. Why is that? Because we're going to call this routine multiple times, and the buffer pointer is not necessarily going to be 0. So issuing a U1 command does not by default reset the buffer pointer to 0. So the buffer pointer could be somewhere random. So we set the buffer pointer to 0. Now, how do we set the buffer pointer? Let's jump down to that routine. Okay, so we push the buffer pointer. So the buffer pointer gets the position of where we want the buffer pointer to be is passed in the accumulator. We push that on the stack just to back it up for a moment. Clear the channel. Check out the logical file number for the command channel. Basic string out the BP command. That's just going to be b-p:. Then we decimal out the command, the logical file number for the memory buffer. This is because you could have, more than one channel open to the device for 2 different memory buffers. So this is the one that this is telling it adjust the buffer pointer for the memory buffer that's associated with this logical file number. Then we output a comma, pull that buffer pointer back off the stack, and do a decimal out. So we've converted the buffer pointer from an int to being like a Petsky number. Okay, so that's going to set the buffer pointer back to 0. So we're going to just go back to our routine at line 202. Okay, so that's going to set the buffer pointer to the start of the new sector that we've just U1'd into the memory buffer. Next, we clear the channel and set the logical file number for the memory buffer to be to read in from that memory buffer. Okay? So because the buffer pointer is 0, we're going to start sequentially reading from 0 and then 1 and then 2 and so on. So we char in the first 2 bytes, and they are the track and sector. But they're the track and sector pointers to the next track and sector, right? We're not there yet, but we will get there. So we read in those 2 bytes, and we store them in next track and sector. Next, we get to the section where we're going to load in a file entry. So we call a routine that says jump to make the buffer pointer, move the buffer pointer for this file name. Now the first time this gets called in a new sector, it's not really necessary because the buffer pointer is already pointed at this. But for all subsequent files, it's going to move the buffer pointer ahead so that it's aligned at the start of the next file entry. So let's just check how that works. So 224 is where we are right now. So BP for FN, go back arrow I, BP for FN, boom. So it's going to load in whatever is our current file name index. Now that index is going to be from 0 to 7. It's going to be less than 8. So all these bits are definitely going to be 0. But the low 3 bits are going to be something from 0 to 7. So we're going to multiply by 32. So in order to do that, we can simply shift 5 times. So that's going to shift these 3 low bits up to these 3 high bits. Okay? That's going to guarantee that this 0 right here is going to end up in the carry. So by the time these 3 bits come up to here, this 0 will get pushed. It's going to go shift 1, 2, 3, 4, 5 and into the carry. So when we're done multiplying by 32, the carry is clear. And we can immediately add 2. Now why do we add 2? That's to skip those 2 reserved bytes at the start of the file entry, as we saw before. And so now that the accumulator is holding the buffer pointer for the file index that we're on, it actually just falls right through, boop, falls right through to set buffer pointer, which we've already looked at. Okay, so we're going to jump back to a number that I can't remember. I think it was 229. Yep, it was. Okay, so that is going to set the buffer pointer for the file index that we're on into this sector. So we're going to clear the channel, and we're going to check in. The buffer logical file number, the memory buffer's logical file number. So we're now going to read from the memory buffer again, but the buffer pointer is in a new place. So the very first byte is the file type byte that holds the lock bit in bit 6. So we load that byte in, and we store it in FType, file type, which was a variable above. The next 2 bytes in the file entry, we can actually go back to our manual here to see what we're looking at. So byte 0 is the file type. So we have these various file types. And it says here, note, file types will be ORed with 80 when the file has been properly closed. File types will be ORed with C0 if the file is locked. So that is to say, if bit 6 is high, the file is locked. So that's byte 0. The next 2 bytes are the track and sector pointers for the first data block that this file points to. We don't need those, so we're going to skip those. And then the next 16 characters are the file name padded with the shifted spaces A0. And then the rest of the directory, the rest of the entry for this file we don't care about. So we've read the first byte that holds the lock bit, stored it in FType. For the track and sector pointers for the data for this file, we skip those. And now we're pointed at the file name. So all we have to do is read in each byte of the file and compare it to each byte in the file name buffer, up to 16 characters. We just match the whole 16. And if we ever encounter one that is not equal, it's not right. It's not the right file. It's not a match. So we're just going to pop down here to not a match. However, if we make it through the entire buffer, and holy crap, the file name is the same in the directory entry as it is in the buffer that we prepared, the file name buffer we prepared, well then it's going to leave this loop right at the bottom and hey, we found a match. And it's going to jump to process this file and then leave the whole routine. But we'll come back to that. Because what's probably going to happen is we're not going to have a matching file name, right? Unless it's the very first file. So it's going to loop through the file name, reading things from the directory entry, comparing against the file name buffer. Whoops. It's going to find something that doesn't match. So that's going to branch down here to no match. So what we do here is we increment the index of the file in this sector. And there are only 8 files in this sector. So we check to see whether our index is less than 8. So if it's 0 up to 7, and if it's less than 8, then we branch back to get the next file name. Okay, so let's do that real quick. Let's just assume that we haven't checked all the files yet. So we're going to branch back up to get the file name. Now what does that do? It's going to call BP for file name. That's going to move the buffer pointer to whatever our new index is that we just incremented. So let's go 1, start from 0. It's going to increment to 1. It's going to move the buffer pointer to where file entry 1 is. That's actually going to skip all that crap at the end of the first file entry that we don't care about. And then it just repeats, checking for that file. And if it's a match, it's a match. But if it's not a match, it keeps incrementing the file index until we hit 8. And then it's like, okay, we still haven't found a match, but we've gone through all the files in this sector. Now what do? Well, we got to move on to the next sector. Okay, so we've already pulled the next track and sector pointers from this track and sector. From this sector, we've already pulled the pointer to the next one. So all we really have to do is copy the next track and sector pointers into the current track and sector pointers and then jump back up to load the track and sector. Just repeat the whole damn thing again. But there is a catch, right? Which is that if the next track pointer is 0, well, there is no new sector to go to. And so if the next track is a 0, we simply branch down here to no sector. If there's no more sectors, we haven't found a matching file yet, and there are no more sectors to search through. So it's going to clear the channel. It's going to read in the buffer's logical file number and call close on it. It's going to close the buffer's logical file number. That's going to deallocate the memory buffer in the storage device. It's going to set the carry because there was an error, and it's going to return. Was unable to make the modification. But if there is another track and sector to go to, next track gets copied into current track, next sector gets copied into current sector, and we jump to load TS. We jump back to load TS. And that is going to reissue the U1 command to read in the newly specified current track and sector. It's going to reset the file index for the new sector to 0. It's going to reset the buffer pointer back to 0. It's going to read in the next track and sector pointers from this new sector. And then it's going to do the loop over the file names in that until eventually it's going to find the file. And when it does find the file index is set. The current track and sector are set. So when it finally finds the file, all the variables that indicate what file entry it is and where it is are already set. And not only that, but the memory buffer already contains the sector that contains this file. So we can jump immediately to this routine called proc file, process the file. Let's go to there, proc file. So proc file, now, as we read through the directory entry to match the file name, we've been moving the buffer pointer sequentially through this file entry. But when we get to the end of the file and it's a match, the buffer pointer needs to be moved back to the beginning of this very directory entry that we were in the middle of parsing. But the file name in sector index is already set. It's the right one. So all we have to do is recall buffer pointer for file name, and it's just going to go boop and move the buffer pointer back to the start of this entry. Okay, that's what the comment says. Set buffer pointer to start of matching file name entry. Next, what do? We clear the channel and we check out the memory buffer's logical file number. Why? So this allows us to, we've set the buffer pointer to exactly the byte we want to modify, and then we've said we want to write to that memory buffer. Now we've already read in the file type. We read it in the first time we read through the file entry, before we even knew if this was going to be the file entry we cared about. We read in its file type. So all we do is we XOR the lock bit, flick the bit, exactly what the CMD and IDE64 L command does, flick the bit, and we char out that file type byte with the lock bit flipped. Now here is where if you wanted to change the file type from program to sequential or sequential to user or something like that, you could also modify the low bits of this file type. I don't know. I mean, maybe I'll do it, but the only problem is that this code only gets called for the legacy devices, and I'd have to add a bunch of extra code to do it for the non-legacy devices, and I don't know how to do it for an IDE64, and it would be even different still for SD2IEC. So It's interesting to note that this is the file type byte, and you could use this to change the file type of the file, but we'll probably just leave it like this for now. So after we've flipped the byte, we can just char out, we flipped the lock bit, we can just char out that file type byte, and it gets written right back to where the buffer pointer had been updated. And then we clear the channel again, because we don't need to write any more data to that buffer, that memory buffer. The only thing we've changed is that one single bit in the middle of that 256 byte buffer. What do we do now? We have to write that entire memory buffer in the drive back to the current track and sector. So we check out the command. We do a checkout on the command channel's logical file number, because the U2 command goes over the command channel. Next, we load a pointer to the U2 command, and we call do-ux command. And the do-ux command, we've already looked at it. It's exactly the same as the U1 command, except that it uses U2. In fact, here it is right here. So it's going to output the U2 command, going to grab the logical file number for the buffer, the memory buffer, decimal out that, send out this comma 0 comma part of the command, and then it uses the current track and current sector, and it outputs those as decimals, and they're exactly the same ones that we just most recently read from. We're going to turn around and use those very same ones to write back out. And so after we have used U2 to write the modified sector back to disk, we simply clear the channel, close the buffer, close the buffer's logical file number. That's going to deallocate the memory buffer in the storage device. We do not have to close the error channel. We clear the carry to indicate that it was a success, and we return. And that's it. So there you go. That's the whole thing. Now, we're at just over we're at 1 hour and 27 minutes. So that's pretty close to where I'm going to stop. I'm not going to bother to describe the process of relocating this library. I've talked about that in other videos, but I will say that when I assemble this, it turns out to be exactly in hex 1F8 in size, which is 504 bytes. It's just shy of 2 pages of memory. And because relocatables are always page aligned, imagine if it was, instead of 504 bytes, imagine if it was 514 bytes, just 2 bytes more than 2 pages. If that were the case, what I would do is I would basically bend over backwards to figure out in the code how to tighten it up to get it to fit within 512 bytes. But as it stands, because it is so close to 512 bytes without going over, that's really good because it makes full use of those 2 pages without very much leftover waste. But there's a little bit like a couple of bytes left over. So if I wanted to stick in a little bit of debug code, like maybe increment the border color just to see what's going on, I could stick that in, and it would still compile, it would still assemble and fit within 2 pages. So it is very convenient that it is so close to exactly 2 pages, but just a hair under. You couldn't ask for anything better. So that is that's the whole routine, and it's been implemented right here, native coding on a Commodore 128 in Turbo Macro Pro for C64 OS. Hope you enjoyed that. See you next time.